Given that a substantial fraction of class might have struggled with Part A, and many did not catch up to finish Parts B and C during the spring break, and perhaps Parts B and C are themselves challenging, there is no need to consider the team bonus project. However, if you enjoy doing extra learning, this presentation shows a number of suggestions for the bonus project. The bonus project is intended for deeper and further learning. It is not something to do just for the sake of extra points. Hence, quality and relevance are essential. If one has constraints of resources and time, it is better to do Parts B and C excellently well, rather than embarking on extra work with the consequence that neither the obligatory parts of the lab, nor the bonus part meets the standard. In other words, at this stage, quality is more important than quantity. On the other hand, you can learn a lot more and have fun with well-designed and well-executed extra work. Hence, treat the followings as either food for thoughts, or exercise for learning enjoyment. This extra learning exercise is to learn how to use the circuit you built, the optical receiver, to do a certain measurements or demonstrations. One suggested demonstration is to answer the question, how does a dimmable LED light change its light output level, such as this small desk lamp? Do not use household LED light bulbs for ceiling or wall mounts. This is an example that is also shown in the video of Lab 4, Parts B and C. This LED desk lamp has 3 levels of lighting. It generates a 3 kHz light pulse signal with increasing pulse duty cycle to go from low, to middle, and high, which is continuous lighting. Go to another video for a similar demonstration with a handheld flashlight. If you have similar LED lamps and/or flashlights, the objective is to answer the question, what do the LED lights do to change their dimmable light output? The following is to discuss other ideas for demonstrations in order to learn more advanced and diverse applications of the optical receiver, beyond this simplistic lighting demonstration. Note, it is not necessary to use or acquire a LED desk lamp or flashlight for a demonstration. The suggested ideas can be grouped into 3 categories. Each has its own video for details. The following is a general description of the categories. The first is to use light to measure mechanical movements. 2 examples shown in the video of Parts B and C are a drill and a blender. Their frequencies were measured by looking at the illuminated light modulation. This is the example with a variable frequency drill. Its highest frequency here is just a bit over 10 Hz. The blender is faster. The backscattered light signal shows the signature of the 2 blades, and its frequency is around few hundred Hz. This approach can be applied to similar objects, such as a fan, or even a person's body motion, such as jogging or cycling on an exercise machine. Or even as simple as waving one's hand or fingers, to see how fast one can do under different conditions such as fully alert, sleepy, or inebriated. One ancient but fun example is the photophone researched by Bell and others in 1880. Sound waves, human voices cause vibrations of a diaphragm, which in turn, modulates the scattering of light beam. A photoreceiver detects this sound vibration and its signal is converted back to sound with a speaker. In a similar vein, one can demonstrate the vibration resonance of an object, such as this spectrum analyzer recording that measures the natural frequency of a wine glass. A speaker can be used to make the wine glass vibrate. The speaker sound frequency can be tuned near the wine glass resonance frequency, and the back reflected light, best done with a laser beam, will show an amplitude resonance at this frequency, like the strobe light demonstration in this video, which was designed to demonstrate the resonance breaking of the glass. It is not necessary to use objects or effects with harmonic oscillation. A different type is to measure the turbulence behavior of a boiling kettle, for example, by observing increasing light fluctuations as a function of water temperature near the boiling point. By taking the power spectral density of the signal, one can observe the 1/f noise behavior. Hence, this is an opportunity to learn or reinforce the concept of power spectral density. Of the remainder two categories, one is particularly relevant to Lab 6 assignment. It is an exercise in signal modulation. It is practically the same as what is done in Part B, but with a twist. Instead, with just one LED, it involves multi-LED frequency division multiplexing. This work helps introduce or reinforce one's knowledge of Fourier analysis, as it involves the use of FFT function. Later, in Lab 6, one will learn the concept of bandpass filter for separating signals with different frequencies. Each category has its own video with further details.